In this video, we're going to have a look at the cos and tan graph. As we did with the sin graph, to determine the shape of the cos graph, we're going to get enough coordinates. My first coordinate is cos of 0 degrees, and that is 1. Cos of 30 degrees is root 3 over 2, which as a decimal is 0,87. Cos of 60 degrees is a half, or 0,5, and cos of 90 is 0. And even though you can continue doing one coordinate at a time like this, you can also use your calculator to determine all the coordinates at once. For this, firstly, we need to make sure the calculator is in the correct mode, which is table mode number 3. Now we need to enter our equation, and that is y is equal to cos of x, which means we need to press alpha and then our closed bracket. Next, you will be asked what the interval is that you are working with. Our table starts at 0 degrees and continues up to 360. And then they ask you for the steps, the increments in your table, and ours are steps of 30 degrees. And now we receive every single y value that goes with a specific x value in our table, and we can simply complete the table. And if you now go and plot each of these coordinates, you will see that again, there's a very clear pattern that is being formed. And if you now connect these coordinates, you will see that it also forms part of a wave. And just like the sin graph, the cos graph is also cyclical and will repeat itself. So this part that looks like a bowl or part of a wave will be repeated in the positive direction as well as in the negative direction. And again, just like with the sin graph, the cos graph has specific coordinates that are important. Firstly, the y-intercept of our mother graph for cos x is at 1, so the coordinate is 0, 1. The x-intercepts are at 90 and 270 degrees. Then in this interval from 0 to 360 degrees, we have 3 turning points. Our first turning point is at 0 degrees and our last turning point at 360 degrees, because at both of these points, if the graph was to continue, it would start decreasing again. The more obvious turning point is the one at 180 degrees. The period of a graph is the number of degrees it takes to complete one full wavelength. For the cos graph, it starts at a maximum of 1 and ends at 1 again before it starts repeating itself. So just like for the sin graph, the period of a cos graph is 360 degrees, after which it will repeat the same pattern. The amplitude is just like with the sin graph, a value of 1, because from our resting position or x-axis, the graph can move up a maximum of 1 or down a maximum of 1 unit. The domain of the graph will once again be determined by the specific interval given in your sketch. On our sketch, we start at an x value of 0 degrees and go up to an x value of 360 degrees. The range of the graph is when you start reading from the minimum value on the y-axis right at the bottom up to the maximum value. And in this case, that means it's all the y values going from -1 at the bottom right up to 1 at the top. Next, we're going to have a look at the mother graph for tan x. And here you can see that the increments in my table are different to the previous two. Here we increase by 2 and 2.5 degrees each time. Starting off with the first one, tan of 0 is 0. Tan of 22.5 is 0,41, and tan of 45 is 1. The tan graph is then the only one of which the mother graph can have a y value bigger than 1. Tan of 76,5 is already 2,41. The important point here, however, is tan of 90 degrees. When you enter tan of 90 on your calculator, you will receive an error message. The reason for this is that the tan graph does not exist at 90 degrees, and therefore the tan graph has an asymptote here. We also saw asymptotes at our exponential graph and hyperbola. An asymptote is a value that the graph moves closer to but never actually touches. If we continue completing our table, the next value, tan of 135, is possible, and that is -1. Tan of 180 is 0, and tan 225 is 1. And then we get to another asymptote at 270, as tan of 270 will give you another error. After the asymptote, we follow the same pattern, with tan of 315 being -1, and tan of 360 is 0. If we now go and plot these points, you will see that we have our vertical asymptote at 90 degrees and another vertical asymptote at 270 degrees. And when connecting these coordinates, you will see that the tan graph increases as it moves closer to our asymptote at 90 degrees. The last y value before the asymptote in our table is already 2,41, and here you can see that as our x value increases and moves closer to 90 degrees, the y value also keeps increasing and moves closer to infinity. Right after this asymptote, our y value starts at -infinity and gradually increases, and just before our next asymptote, it once again tends to positive infinity. And again, after this asymptote, it starts at -infinity and moves upwards. Note that the tan graph is not a straight line, but that in between two of these asymptotes, there will always be a curve that starts in the bottom left and with one curve moves its way up to the top right. And this pattern keeps repeating. So, to the right of what we've already drawn, as well as to the left of that, this pattern will be repeated. So the tan graph intercepts the y-axis at 0, 0, which is also one of our x-intercepts. And after this, the graph intersects the x-axis again every 180 degrees. Because the tan graph keeps increasing, it has no turning point. And this also means that it doesn't have an amplitude, as there is no maximum or minimum value. The period of a tan graph is the time it takes between two asymptotes to form the curve, and that is 180 degrees. And even though in this case our domain is still all values from 0 degrees up to 360 degrees, for the tan graph we need to specify that it cannot be the x value of the asymptotes at 90 or 270 degrees. And finally, because the tan graph does not have a maximum or minimum value, but continues upwards and downwards forever, it will consist of all the y values. In the first two videos, we had an in-depth look at the mother graph for sin, cos, and tan. In the next few videos, we'll have a look at the transformations that these three graphs can undergo.